Hi, this is a presentation about Linux containers and specifically about Docker, a new project that makes it easy to manage your Linux containers, create and destroy them. Uh, so because I'm trying to this presentation to just 30 minutes, I'll keep it short. I'll try to. So this is the high level picture of what Linux containers are. So here's your kernel, the Linux kernel. By the way, this solution is Linux only, so it doesn't work with any other operating system, no Windows, no Mac OS support, no FreeBSD. But those OSs do have their own container like implementations. So for now, we are working with Linux containers only. So this is a presentation about that. So here's your Linux kernel. That provides all kinds of services that your applications use, your servers, your daemons use to talk to the rest of the world. It has CPU, it has memory, it has file system, and it has network, which I haven't drawn over here. So those are the four basic resources that a computer provides. And Linux kernel basically provides all these services via APIs. So to provide a virtualization solution on top of this, people have all kinds of virtualization software that act like hypervisors or like complete desktop level virtualization emulation of OS and hardware. But Linux container is a little bit different because it's implemented inside the Linux kernel. So containers is not really a big feature, but it's a coupling of a few other features combined together, and they provide the ability to create containers. So the facility or the implementation within kernel is called C groups or control groups, and there are quite a lot of control groups that are implemented in Linux, and they provide isolation or control over the various resources that the kernel provides. So to have a look of what kind of container groups we have, let's just see at the mount command. So you can see the C group over here. There is one C group for CPU set, which CPU's process can access, can be limited by this C group. Number of consumption of CPU can be limited by this C group. CPU accounting, memory devices, freezer, block IO access, huge TLB. So these are the various resources that you can control for specific containers. And Linux containers are basically a combination of all these control groups. So that's basically very short version of what Linux containers are. And this is just a visualization of what a container container looks like. When Linux community started implementing containers or these isolation features, C groups, they did not visualize it as containers that are shipped across oceans on the ships. But along came a company called .cloud, and they had an internal project for like cloud deployment, etc., using Linux containers. So they had a small project, internal in-home project called Docker, which they thought of like open sourcing so that it can be used by others. God bless them. And like over the next few months, within like first 2 to 3 months, it became a huge hit, and people started using it left and right, and they have actually spun off a new company called Docker.com just based on this. So Docker took this idea of containers and mapped it to the real world, where you create containers, shipping containers. They are isolated units of storage, and whatever they contain inside doesn't matter, but they can be put on ships and sent across to another country, another place. So they just took that metaphorical approach to that, and they simply started using that image. So yeah, in a nutshell, what Docker daemon does is it creates Linux images for you, and it allows you to run those images as containers. So it allows containerization of your utilities. So here's a high-level architecture of Docker. So Docker, there's always a daemon running on the operating system, on the OS where you want containerization to happen. And then there's a client utility by the same name, Docker, that talks to this daemon over HTTP. So this is a nice kind of isolation where you can run your client on a remote machine as well, but control the daemon on the local machine. And this client is completely isolated. This daemon doesn't have any access to what this client has access to. So any command or any data that this client wants to send, let's say it wants to create a new container using PostgreSQL binaries or something like that, it will have to compress that or wrap that up into a tar file, send that tar file over HTTP to the daemon, and then the daemon will use that tar file to create a container image. So that's like very high level picture of how Docker works. One nice thing that just came to mind about containers is that it is multi-level containerization or virtualization solution. That means you may be running one version of kernel in one container on this primary kernel, but within that container you can go ahead and create another container or another virtual machine of its own. So you can create a whole tree of virtual machines that are isolated from each other, and they basically behave as if within the controls, within the limits put on top of their parent container by the C group implementations. So, and creating and destroying containers is almost instantaneous, because all that it is doing is creating a new process and limiting its ability to look at other processes, other file system components that you want to control, or how much memory it wants to consume, how much CPU it can consume, or which CPUs it can run on, and then what kind of network access it has. So containers is basically just limiting the facilities provided to the process. So that's why it's very, very fast. But the downside is that this solution is not available as a general virtualization solution for any other OS. All right, so I think we are close to the mark. On to an example of, so these are the commands. Before I show you an example or an actual demo, these are the commands. Docker build, basically it takes a Docker file. It's kind of a special kind of script. It has its own command set. So it takes that file and creates an image for you. So that's the dotted line that is showing you an image. But it's basically, an image is basically a tar file or a set of contents of a file system at a specific time that are tarred up and stored as a single bundle. So image is actually almost equivalent to your operating system, but not really an operating system, completely installed operating system, because it doesn't have a kernel. All the kernel facilities are provided by the base kernel. You cannot install your own kernel within a container. That's a limitation also. So all the facilities are provided by the kernel that's at the base of this whole tree of containers. And you cannot create your own Linux kernel inside it, and like if you wanted to install, let's say, a development version of Linux kernel, you can't do that in Linux containers. So image is basically a snapshot of file system at a specific time that can be used to create containers. So that's an image. And then the other command in Docker is docker run. So docker run takes this image and creates a container. So basically docker run tells the daemon to run a container, and image is basically stored on the daemon side. That means that the client gives the Docker daemon a lot of commands how to create next version of the image, and it creates that image continuously. With every command there is a new image created, and when a final image is reached, as a user I'll tell Docker to use that image to run a container. So that's where this command docker run is used. So the client sent this command to the Docker daemon, and Docker daemon will launch a container. And Docker daemon doesn't need to be running all the time, because once you launch a container, Docker daemon service can be shut down. The container will continue to run because it's controlled by the operating system, but not by Docker. So Docker is not actually anywhere related to Linux containers. It's only an ease of use. It's only making it easy for you to use Linux containers, create containers and manage them. So you can shut down Docker daemon, and the Linux containers that were created by it will continue to run. So with that, let's go into an actual example. So I don't have anything ready for this demo or specific for this demo, so I'm going to use something that I'm actually using here. So this is an example of a Docker file. So what it says is the first command, anything that starts with a hash is actually a command just like any other shell script. And the other commands are basically canonically written in uppercase, but they are not case sensitive, just to as a visual aid for us to say that this is a command. So we write it in uppercase, but it can be a lowercase as well. So from is a command that says take this as your base image, and this is something that you already have. So let's go over this quickly, and then I'll give you actually show you where that CentOS lives. So take this image CentOS. This is just a marker that says who is the maintainer of this Docker file. Take that image CentOS and run this command yum update -y. So update all the yum packages in CentOS, and then run a command printf, emit that information into pps repo, a file that I'm trying to create, and then run yum install pps9 to yum install OpenSSH server, etc. So just run these commands. So what happens is every time a command is run, Docker takes the previous version of the image and runs that command, the command that you're trying to execute, let's say this command, and the changes that were done by this command are persisted into file system, and a snapshot of that file system is used to build the next image. So now after running this command, it has already created an image for you, an intermediate image, and the next command will be used on top of that intermediate image. And when this command finishes, another version of the image has been created, a new image has been created. So the previous image already exists, and this also creates another image. So every command that you run creates an image in the background, and it keeps track of which commands were used to generate which images. Because if you were to run this Docker file again, it will not actually do all of this work all over again. It will instead use the cached version of that image. So let's say you ran this whole Docker file once, and then 2 minutes later you made some change, let's say, and at this line you wanted to run echo hello world. For some reason you wanted to echo hello world. So in that case, it will not do anything until it encounters a new command. All these commands have actually resulted in some specific images. Those images will be reused from the cache. It will not have to do all these install yum update -y installation of these packages. But the moment it encounters a command, a new command, corresponding to which you do not have an image already, now it will use the image from this command's result and create a new image for you, and the rest of the commands will now be using that image that was created by this command. So that's kind of a nifty way of speeding up the image build process, and it almost works like your Git internals. If you are aware of Git, it has a object tree, which each object of within that tree has a SHA-1 ID. So this also works on the same principle. Each command that you run creates an image. An image has a SHA-1 ID, and it's uniquely generated based on all the commands that were run before generating that image. So this is what Docker file looks like, and then you can go ahead and read through the documentation of Docker, what all these commands mean. There are a few important commands that you may want to learn about. So one is simple run. The other is expose. So expose says expose port number 22 from this container. So now the outside world can talk to this container. Otherwise, only the container can initiate network communications. But I wanted to run SSHD. As you can see over here, I'm installing SSH server, and I want my host system where I'm running this container to be able to talk to this container. So I run SSH server on within this container and then expose port 22, and then I can use that port 22 from outside the container to talk to the container. So that's an example of the Docker file. Let's now see output of some commands. So docker ps. So you'll see that there are no ps simply says process status, just like your Linux ps command. It shows you all the running containers, but it does. I currently don't have any running containers, so I'm going to say -a to show all the dead containers as well. So those are the containers that have been created in the past and then destroyed. And so you can see the status of this one, and the other one is docker images. So when you build an image, you have to give it a name. So I'm using that Docker file that I just showed you for XDB testing, and I create a base image and then I create a final test image based on that. And for building the base image, I use CentOS as the base. And here you can see some initial operating system installations are provided by default. So you can choose one of these versions. You can say I want CentOS 6.4. You can see 6.4 and latest have the same SHA-1 ID. So this is the truncated version of the SHA-1 ID, but it actually has the full length SHA-1 ID. I think it's 64-bit, 64 characters or so. I'm not sure. So that's the list of images currently installed on this machine. And if you do not have an image that's like supposed to be provided by Docker, it's actually stored in index, index.docker.io. And if you say for the first time, let's say if you were running that Docker file from CentOS do this, it will actually download CentOS image from the Docker index, because that's where the base image is stored. And then from that CentOS, it will build your next version of the image that you want to run. So I have a few images running over here. So as and when you build new images, and if you give a new image the same name as was given to the previous, it will mark the previous image as without any name and move that name to the newer image. So, and then there's a new version, like the latest version I'm running is 0.7.1. And that has the ability to show you the tree of images. So this might help you understand what it actually looks like. So let's see where our XDBA test is. So that is the image that I use for XDB testing. And you can see XDBA test is derived from XDBA base, and XDBA base is derived from one of these intermediate versions of some other images, which actually lead up to this image, which is derived from CentOS 6.4. So this might give you a visual representation of what this Docker is actually doing behind the scenes. And every time you run a command, it uses a base image and creates a new image. You run a new command on top of that, it will take a base image and run a new image. So that's how you get your images, intermediate images, and the final built image. So to do that, you have this command called docker build, and -t is the tag to assign a tag. So So -t to assign a name, a repository that says, and with an optional tag. So I don't use any repositories, I only use tag parts of it. And that's how you create an image. And let's take an example of how to run this image and how fast this solution is. So this is the command that I use docker run, keep this std in open, keep std, use this tag and run a command /bin/bash from inside that container. So let's see what does docker look like right now, the docker tree. So here it is, there's nothing under docker right now, and now we are going to run docker one container, and there it is, like my virtual machine is ready. And these are all the processes within the virtual machine. You can see that process ID 1, which is usually init process in normal kernels, but in my case, within the kernel, within the container, it's just the bash command. And let's run sleep command and see what does it look like from outside the container. So now let's run the ps output again, look for docker, and you can see that docker daemon started lxc start. This is Linux containers, and it used an image to launch that container. This is the configuration of that container, so you didn't have to do any of that. And how to start that container, the initial image, etc., and run a bash command inside that. And within that bash command, I'm running the sleep command 1002, and I can inspect this container from outside the container as it is. So that's the advantage of Linux containers, and I hope I showed you just enough to get your interest in Linux containers. It's fast, it's easy now given docker.io, and it's like almost free. There is no overhead in terms of performance. You can create any number of containers parallelly and run them as long as they are not like bogging down your whole OS. And you can limit their consumption, the resource consumption at container level. And they can't see anything that you do not want them to see. So here it is. Let's run this command again and see what that ps looks like from inside the container. And over here you can see that there's basically just 3 processes running. One of them was the ps command that we just ran. So there it is, Linux containers for you. Go ahead and try installing it from docker.io. I would suggest using Linux version 13.10, and but right now I'm using 12.04, Ubuntu 12.04, not 13.10. If you want to run it on 12.04, you'll have to install like newer version of kernel that comes with 13.10, but backported to 12.04. But if you start with Ubuntu 13.04, you'll be just fine. And with the latest release 0.7, Docker is now capable of running on CentOS, Fedora, etc., etc. I haven't tried that, but feel free to do that. Try it on any Linux. It is supposed to work on any Linux now, because earlier it had a limitation that it needed AUFS, an abstraction layer, to control the file system. But now that limitation has been lifted, because now it supports a few more file system types. And I'm working on ZFS file system support for Docker. So yeah, go give it a try. It should work using at least VFS, or if you have Logical Volume Manager 2, LVM2 installed, it should be able to use that. And all right, let me know if you have any questions, and have fun with the containers. Bye.